So if we have a GARCH11 model, we are saying that our volatility is essentially depending on three main components. That is to say, this long-run value, what happened yesterday in terms of returns, of squared returns. So when you take the square of a random variable, essentially you're already playing with the variability of that random variable, and with the value of the volatility itself. We're assuming a convex linear combination, so gamma, alpha, and beta, they all sum to 1. Now, already here, without being too technical, we have an assumption, which is not as strong as assuming IAD and the fact that you take the sigma, the square root of t. But you are assuming that on the market there is some sort of long-run value, the long-run variance, and then you take the square root of the long-run volatility. That is some sort of physiological quantity for the market. That is to say that if we imagine to remove all the oscillations, all the small changes induced by the fact that we trade and we interact on the market, it exists for some reason. And obviously there are economic theories that tend to give a justification for this quantity, so the fact that it might exist. There are people that agree on the fact that it might exist, and people that are not in line with that idea. So also there are nevertheless assumptions. Now assume that we have somehow correctly estimated the parameters of a GARCH11. You can have an entire course on the GARCH model, so nevertheless, we have estimated the parameters. Omega is 0.02, alpha is 0.03, and beta is 0.95. And we have a certain number of questions that we want to answer. The first one is, what is the long-run average volatility? So can we estimate that quantity? The second one is, today we know that the volatility, as we can see that from our data set, is 1.5% daily, and we want to get an estimate of the volatility in 20 and 60 days. So we want to have an estimate of volatility in 20, 60 days without using the square root of 20 and the square root of 60. But since we believe that our GARCH11 model is correct, we want to use the GARCH11 model. And another interesting situation, this is, for example, interesting when you have stress test and the scenarios that you can try to generate to see what happens on your portfolio or to your bank or to your company if there are changes in different quantities on the market, and is the following. Suppose that there is an event that increases the volatility from 1.5 daily to 2% daily. What happens in 20 days from now? Okay, so we are making some sort of scenario. Now, the first answer is simple, in the sense that we want to get VL, which is the long-run variance, and take the square root to have the long-run volatility. Now, you recall that VL is gamma VL in our representation. But I also told you that very often when a computer program, so for example R, also Python, depending on the package you use, you get the omega, not the gamma. So you have to extrapolate VL from that. So if omega is 0.000002, we have to extract VL from that quantities. How can we do that? We can exploit the fact that by construction in this model, gamma, alpha, and beta sum to 1. So what I have to do, since I know that omega is gamma VL, and I know that gamma plus alpha plus beta sum to 1, I can get my VL by dividing omega by gamma. And since I know that gamma together with the other sum to 1, and I don't know gamma, gamma will be just 1 minus alpha minus beta. Okay? So if I take omega divided by 1 minus alpha minus beta, It's like playing with the three cards, okay? So omega divided by 1 minus alpha minus beta is 0.0000 blah 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 2 divided 0.02, which is 1 minus 0.95 minus 0.03, okay? If I do that, I have that the long run variance is 0.0001. Now, I'm asked to compute the long run volatility, so I just take the square root. And the long run volatility is 1%. It means that if this model is correct and my estimations are correct, according to my model, the volatility I can expect on the very long run on the market is 1%. What the long run means will depend on the model, but let's say it's something like 1 year from now, okay, or a little bit more. To solve the second and the third point, we need a little bit more complicated tool. So, if there are mathematicians in the audience, and I know that because I recognize the faces, it's a nice exercise to try to derive this formula, so you don't get bored by the fact that you get all the formulas without deriving them. But otherwise, we can use this formula in which we can try to get the expected value of the volatility in t days from now. So today we are at day n, and we want to make a prediction of the expected value in t days from now. Now, this value is relatively simple in the sense that it will be, by definition, the long run quantity, which is always there, okay, plus an addition, plus a term that we add to that, which is alpha plus beta to the power of t, multiplying the difference between the variance as we have estimated in day n minus VL, the long run variance. Now, again, I am not interested in the derivation of this formula. It's a nice exercise. You can also find the details in the book, but as you will see, also on the sections I assigned you to read, you can jump over that section. Now, if we apply this formula, what we have is that we want to make prediction in 20 days from now. Okay, since our unit of time are days, 20 is 20 days from now. So applying the formula, what we have 0.001, which is the long run variance we have obtained by the model, from the model, plus 0.98, which is alpha plus beta, to the power of t, 20, multiplying what? The difference between the variance today, and in our text it was 1.5% in terms of volatility, so the variance is the power of 2. So 0.015 to the power of 2 minus the long run variance, 0.0001. You compute, and the value that you get on the right-hand side is our value. This is the variance, so I take the square root. And the value that I obtain is 1.35%. So in 20 days from now, if my model is correct, I can expect a volatility of 1.35. Now, if you take 60, it's exactly the same computation, but there, instead of 20, you have 60. You do the same exact step, and you get that the volatility now is 1.17. Already moving from 20 to 60, you see that there is a decrease from 1.35 to 1.17. Why? Because by construction in this model, you will reverse, you will converge towards the long run volatility that for us was 1%. So if instead of 60 you take 90, you will see that you will be closer to 1%. If you take 100, you will be even closer to 1%, and so on. In the limit, it will be 1%. If you want to answer, on the contrary, the other question, what we have to do, instead of using 1.5%, we substitute 2% in the formula. So the first part remains the same, the long run variance, 0.98 remains the same to the power of 20, And instead of 0.015 to the power of 2, I now have 0.02 to the power of 2. The rest remains the same. And what I get is that the value I obtain is the variance, square root, and the volatility will be 1.73, which makes sense. So if I observe a jump in the volatility, I can expect that the model will keep memory of that jump in the future. So now the expected volatility in 20 days is 1.73. It was 1.35, but because of the jump that we observe today, or that we are assuming to observe, we are making a scenario, we can expect the volatility in 20 days to be 1.73. Okay? Now, once we have defined volatility in this way, we will see that this quantity and the fact that it is computed in a way or in the other has a lot of consequences for our modeling choices. We will see, for example, that volatility and the way in which it is computed affects very important measures of risk that we will introduce tomorrow, like the value at risk and the expected shortfall. And since those measures of risk are imposed by the regulator, that we will see is the Basel Committee on Banking Supervision, on banks, in order to decide how they have to handle their reserves, the way in which they do business, a very simple number, like sigma, if it is wrong, has serious consequences on the rest. The wrongness of that estimate will affect other measures, like the value at risk, like, for example, the expected shortfall, like many other things. And those numbers are used by the regulator, the National Bank of the Netherlands, the National Bank of Spain, of Italy, of France, of Germany, the European Central Bank, if it is a systemic bank, the Federal Reserve, if it is a US systemic bank, the Bank of China, if it is in China, whatever. They will use those numbers to say, you can do that, you cannot do this. You can lend more money, you have to reduce the amount of lending. And all these kind of things have important consequences on the economy. So just starting from a small, stupid sigma. Okay? So it's not so irrelevant to know how these quantities are computed and what impacts they have. And I hope that tomorrow it will be a little bit more clear already with the value at risk. At the end of the day, we will play with a formula, which is, again, not particularly complicated. That is this. Ignore for a second this and this. You see that your sigma is here. And if this number is wrong, the total is likely to be wrong. And that total is an important number in terms of regulatory capital and blah, blah, blah. Now we have enough time. I have enough time to bother you with these kind of things. The topic that we introduce now, which is fundamental for what we will see tomorrow and in the next classes actually, is the one of coherent risk measures. Now, this topic is also treated in the book by Hall, but I don't like the way in which it is treated. So, for me, it is sufficient that you know what's on the slides. Okay? So, for that, you will see that I'm not referring to any of the sections. And you will find extra, essentially from tomorrow, you will see that on the course platform, you will also find videos and extra stuff that can help you in complementing these kind of things. Now, in risk management, the topic of coherent risk measures is extremely relevant. In my opinion, is not as fundamental as they want it to be, but still it's very important. Now, what is a risk measure? I told you the first day that we need tools as risk managers in order to perform and to reach the goals of risk management. which are exactly identify, assess, and prioritize the different type of risks. Now, risk measures are the tools that allow us to identify and assess. Okay, prioritize, then it's something that depends on our on our beliefs, on our constraints, and so on. But essentially, we need measures, we need numbers that can help us in saying that something is riskier or less risky than something else. Okay? Now, a risk measure is very simply a quantity that we use, a tool actually, that we use to quantify risk. We will see that, for example, risk measures as the valued risk and expected shortfall are risk measures that are even used to quantify the amount of capital that I have to put aside as a reserve, as a hedge for risk. But we already saw that, because when we were hedging using the Greeks, in order to delta hedge, gamma hedge, beta hedge, or whatever hedge you want to do, you are quantify the risk, delta, gamma, and then you build a strategy in order to try to neutralize that, at least partially. Now, you could be extremely technical here, because, for example, from a mathematical point of view, we should define, and this is what I do in other courses, you should define the properties of the risk measures in very precise terms, but not only the properties. A risk measure is a map, so it's a function that maps from different spaces. What type of spaces? You introduce the convex hull, and blah, blah, blah. But we don't care. So what we do here is to say that it's a tool that we use to quantify risk. And if this tool satisfies a certain number of properties that are mathematical, but most of all economical, so they have a strong economic and financial interpretation, we will call it coherent. Okay, so a coherent risk measure is just a specific type of measure. A coherent risk measure is, in practice, a measure that satisfies these four properties. It allows us, as we want to be able, to prioritize the risks. That is to say, it allows us to have an ordering of the risks. That is to say, this is riskier than this. Very simple. So we want to be able to prioritize risks. And it makes sense. I mean, otherwise, what's the purpose of that? It exhibits somehow a proportionality to risk. What does it mean? It means that, very naively, if I have a portfolio that has a certain amount of risk in it, for the moment it does not matter how I have computed that, but say it's a number, 100, okay? I want to know what happens if I double the size of the portfolio. Okay, if I double, my portfolio was 1 million with a risk of 100, what happens if I build a portfolio that now is 1.5 million or 2 million? What happens to the associated risk? It will not stay to 100, and I want to know what happens. And I want that to be somehow proportional. I want a risk measure that is neutral to things that are perceived as non-risky. So I want a risk measure such that if I have my portfolio and I add the risk-free asset, or I add cash, so money out of my pocket in the portfolio, and I assume that I'm on a relatively short time horizon in which inflation is nothing particularly relevant. Okay, we are not in Zimbabwe, we are in the Netherlands, so inflation is under control. If you are in Switzerland, even better, inflation essentially does not exist. So what happens is that 100 euros are 100 euros, today and tomorrow. Maybe in 20 years, it's not the same purchasing power, but now it's exactly the same amount. So I want a risk measure that if I add 100 euros in cash, does not change. Why? Because there is no risk in adding cash to the portfolio. Okay? We will see that we can even think that the risk measure decreases instead of remaining the same. Why? Because you can always say that the cash you are adding to the portfolio is already part of the capital that you are using to hedge the risk. Okay? And finally, we know that in every course in finance, but I think also when you are at the elementary school, everyone tells you that it's not very clever, it's not very safe to put all your money in one investment, but it's safer to diversify, so to split your money into different investments, so that if you build a nice portfolio, you can have bad luck on one of the investments, but still you are okay on the others. Or you can also build a portfolio such that if something goes bad in one direction, it is compensated in the other direction by some other assets. Okay? So we want something that gives incentives to diversification of risk. Now, these four economic, meaningful properties that we want for a risk measure can be translated into mathematical properties that are the following. The fact that we have a possibility of build a ranking of risks and prioritize risk is what we will call monotonicity. So I want a risk measure such that if the risk increases, the risk measure increases. I don't want a function that goes up and down, up and down, up and down without any particular meaning. I want something that is positive homogeneous, so positive homogeneity. That means that there is this proportionality in the risk. I want something that is translation invariant. That is to say, if I have a portfolio and I add something that is not risky, that does not affect the portfolio or even reduces risk. And I want something, which is very important, that is subadditive, in the sense that if I add different type of assets, the total risk of my portfolio should be smaller than the sum of the risks of the assets. So let's see in a little bit more formal terms. So I have a risk measure that I call phi, okay? So phi is, for example, the standard deviation, is the delta, is the variance risk, is the expected shortfall, is the new fantastic risk measure you have invented 3 seconds ago. Okay? Now, I want this risk measure to be monotone, subadditive, positive homogeneous, and translation invariant. What does it mean? Assume that Z1 and Z2 are two random quantities that represent, for example, my losses or my risk. For us, namely, as I told you in the first class, risk is what? The probability of a loss which is higher than what we were expecting, or a profit, a return, which is lower than what we were expecting. Let's say that Z1, Z2 are losses. They belong to a space. That's the strange L that you see, but we don't care about that. So we have these two losses. And we want to have this property. If Z1 is less risky than Z2, then the number that my measure phi assigns to Z1 needs to be smaller than the risk it assigns to Z2. Trivially like that. So if you recall the efficient frontier that we saw with Markowitz, the capital asset pricing model, and now we can start building the connections, what we were saying? We were saying that in our graph, we had the standard deviation, the return. On the efficient frontier, we had all the portfolio that were maximizing the return given a level of the standard deviation. But we also knew that if I was taking two different standard deviations, the higher was perceived as riskier. So in order to compensate someone to take a higher risk, you would give a higher return. Otherwise, it would not be rational, whatever rationality means, at least in this framework. So monotonicity means that if the risk increases, the number the risk measure assigns to the risk increases trivially. Subadditivity means the following. I have the sum of my random variable, and if I apply phi to the sum, that needs to be smaller than equal to the sum of the risks applied to the single random variable. So if I build a portfolio, I want the risk of the portfolio to be smaller than equal to the sum of the risks. This is what we call subadditivity. If it were just equal, that would be additivity. If it were bigger than, greater than, would be superadditivity. Now, subadditivity means that the risk of of the sum is smaller than the sum of the risks. Then we have positive homogeneity. It means that if I have a constant, A, which is positive, and I inflate my portfolio for that constant, essentially I'm multiplying by that constant my risk. It means that if I have a portfolio that generates losses Z, and I double the portfolio, I can expect double the losses. Okay? As simple as that. And double the risk. Finally, there is the translation invariance. Don't be scared. I mean, if you spend 5 minutes, I hope already now, but if you spend 5 minutes, it's just a formal way of writing something actually trivial. If you have B, which is, again, a constant, which is perceived as non-risky, and for us it can be the risk-free asset or cash, assuming inflation does not count, and blah, blah, blah. What I'm saying is that if I have my portfolio and I add cash onto that, the total risk, phi of Z plus B, needs to be phi of Z. So the total risk does not change. Or, you see in the brackets here, dots minus B, it means that in some specific situations, you can even think that the risk decreases. Why? Because your cash that you are adding to the portfolio is already part of that capital that you will use to hedge the risk. So we will be a little bit more precise later, because the last the last property, translation invariance, can be actually declined in different ways depending on the type of risk measure that we use. So if a risk measure satisfies these 4 properties, it's called coherent. Sometimes they add a 5th property, which is not nevertheless necessary for coherence. That is to say that if I have something that is non-risky, the measure assigns value 0 to that. Okay? But this is just a convention. I could also say that, okay, for me, if something is non-risky, the value is 100, and all the other values will be larger than 100. Okay? So it's not fundamental. Now, coherent risk measures are extremely important in risk management. We will see that. But today we were speaking about what? We were speaking about volatility. Okay? And I said to you that a convention is to use the standard deviation as an estimate of volatility. But it's a convention. So I told you that in certain situations, as I will try to show you, is not even a clever choice. But one thing that we could ask ourselves immediately is the following. When I study statistics, the first time, the teacher is bothering me with different quantities: the mean, the variance, the standard deviation, the covariance, the correlation. And we know that if we take the variance and the standard deviation, the variance is sigma squared, the standard deviation is sigma, because one is the square root of the other, or one is the power 2 of the other. So the question could be, why do we use the standard deviation or the variance? Essentially, they give us the same information. Okay, it's just a matter of taking the square root. Apart from that, if I have a variance of 100 or a standard deviation of 10, should provide me, apart from the scale, the same information. Okay, one of the justifications for which we choose standard deviation over the variance as a measure of volatility, as a possible measure of volatility, is the fact that the standard deviation is a coherent risk measure, the variance it is not. So let's try to see why. Now, we will do that together now in class, but on Brightspace you also find all the details again. Now, to show that a risk measure is coherent, we have to prove that it satisfies the different properties. Now, to prove that the standard deviation and the variance are monotone, in that sense, mathematically speaking, it can be done without further assumptions, but since it's complicated for us, we assume that we are in the efficient frontier framework. And in the efficient frontier framework, since we use the standard deviation or the variance as measure of risk, we know that if you are a rational operator, a rational agent, essentially the higher the variance or the higher the standard deviation, the higher the risk. So in the framework of the efficient frontier, essentially monotonicity is a gift that you get for granted. There is nothing to show. You find some little more details on bright space. But we can say, okay, we assume that monotonicity holds and it works. But what happened with the other properties? Let's start, for example, from translation invariance. Now, imagine that I have a random variable x with a variance x, okay? Now, what I want to show is what happens if I take x plus b, where b is not a random variable, but it's just a number as a constant. So, what do we know about the variance of this? If I have the variance of a random variable and I add a constant, what's the result on the variance? What's the variance of x plus b? It's just the variance of x. Correct. So the variance is translation invariant. I can add a constant and the variance does not change. So the variance is translation invariant. And if I have the standard deviation, again, so you can do that using the property of the standard deviation, or you just recall that you take the square root. So also the standard deviation is translation invariant. So that property, it's okay for both. So for the moment, they are both monotone and translation invariant. Let's see, for example, if they are positive homogeneous. So what I have is that I am in this framework, and now I want to study the variance of AX, where A, again, is a constant. What's the variance of that? Do you recall? Yes? It's A squared, the variance of X. So it's A squared, the variance of X. But A squared, the variance of X, is not A, the variance of X. It's different. So you have a square in the A. So the variance is not translation invariant. Sorry, it's not translation invariant. It's not positive homogeneous. Sorry, it's not positive homogeneous. Is the standard deviation positive homogeneous? Yes, it is. Why? Because the standard deviation of x is equal to the square root of this. But the square root of this is the square root of this. And the square root of this is a, the standard deviation of x. Because it's the square root of a squared, which is a, and the square root of the variance, which is the standard deviation. So the standard deviation is positive homogeneous. If you want to be particularly pedantic, it's positive homogeneous of order 1. But for us, it's just positive homogeneous. So already here, you can stop and say the variance is not coherent, because it violates one of the properties. It's not positive homogeneous. But the variance is also not subadditive, while the standard deviation is subadditive. How can we see that? It is rather simple. So now we need another random variable. Let's call that y, and that we have the variance of y. Now imagine that I want to compute the variance, which is subadditivity, of x plus y. Now, what's the variance of x plus y? We know that is the variance of x plus the variance of y, and if x and y are independent or uncorrelated, I can stop there. But I'm not saying anything about x and y. They can be dependent, and actually, in financial assets, most of the time, they will be dependent. So the general result needs to take into consideration what? the covariance. So you have plus 2 times the covariance between x and y. Or if you want, you can write this as the variance of x plus the variance of y plus 2 times the correlation of x and y, the standard deviation of x, the standard deviation of y. Why? Because the covariance between x and y is just, because the correlation between x and y is just the covariance between x and y divided by the product of the standard deviations. Now, if this quantity is positive, if it is equal to 0, what do I have? I have that the variance of the sum is just the sum of the variances. So in principle, yes, it is true that it is subadditive. It is subadditive with equal sign, but still, it's fine. If the covariance is positive, then this quantity here is more than the sum of the variances. So it is not subadditive. If the covariance is negative, it is subadditive. But in general, it is not, because it all depends on this. So in general terms, the variance is not subadditive. What happens to the standard deviation? Now, let's continue from this equation. Okay, so I have the variance of x, the variance of y, plus 2 times the correlation between x and y, the standard deviation of x, the standard deviation of y. Now, what do I know about correlation? Now, let's consider covariance and correlation. Covariance is a measure of the linear dependence between x and y. What do I know about the covariance? What's the range of variation of covariance? Can covariance be 0? Yes, if they are independent or correlated, it's 0. Can be positive? Yes. Can be negative? Yes. Can be plus 10? Yes. Can be 100? Yes. So what's the maximum value the covariance can attain? Essentially plus infinity. What's the minimum value? Minus infinity. The covariance is between minus infinity and plus infinity. Okay? That's the range of variation of covariance. What about the correlation, conversely? The correlation is, again, a quantity that is positive, negative, or equal to 0. Again, it's linked to the covariance, so it inherits the sign of the covariance. These quantities are standard deviation, so by definition are positive. This can be positive, negative, so also this one can be positive and negative. But the range of variation of the correlation is different. Correlation can be 0, can be positive, can be negative, but what's the maximum value correlation can attain? 1. What's the minimum value correlation can attain? Minus 1. So correlation lives in the interval minus 1, 1. That's why we tend to play with that. It's easier to play with minus 1, 1 instead of plus infinity, minus infinity. Now, if it is between minus 1 and 1, I can take the maximum value, which is 1, and say that this quantity here will always be smaller than equal to what? The same quantity, so the variance of x plus the variance of y plus 2 times the correlation in its maximum value, 1. So times 1 times the standard deviation of x, the standard deviation of y. I've just substituted 1 here because I'm taking the maximum value that the correlation can attain, which is 1. If I do that, now allow me to be over pedantic and say that the variance is the standard deviation of x squared plus the standard deviation of y squared plus 2 times the standard deviation of x, the standard deviation of y. Yeah? But this is equal to what? To the standard deviation of x plus the standard deviation of y squared. You agree with me? Okay, we started from this. I take the square root here, and this is the standard deviation of x plus y. I take the square root here. 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 And I take the square root here, which is the standard deviation of x plus the standard deviation of y. But we have the small term equal to here. So the standard deviation of x plus y is smaller than equal to the standard deviation of x plus the standard deviation of y. The standard deviation is subadditive. The variance is not. So the standard deviation is monotone, positive homogeneous, translation invariant, and subadditive. It's coherent. That's why we use the standard deviation when it works. So see you tomorrow.